Oh, we'll get started here in about 2 to 3 minutes. Thanks for your patience. We'll get started in just a minute. Thanks for your patience. All right, everybody. Thanks for joining in today. Could someone kindly let me know if you're seeing the course home screen?
Yes, ma'am.
Thank you very much. So this is for the benefit of anyone who is in the 11:30 lab today. I did post an announcement on Canvas saying that we would not be meeting today for lab. We will meet on Thursday, okay? But I did post that in an announcement yesterday, so hopefully you got around to seeing it. Just want to do a quick peek regarding the announcements. Let's see if I go in student mode just for a second. So I did post the video from the videos from last week, just in case you were looking for them. I got a couple of emails asking where to find them. So just as a reminder, the class recordings are always in the announcements. So that's where you can go and look to see those at any point. Okay. All right, let's get into the weekly overview. Oh, bear with me for just a second. I always forget that I have to log in to Nunez if I want to see the Nunez items. So sorry about that. Now you should be, let me go back and share. Okay, so now we should be all seeing the weekly overviews. And if you scroll down, sorry, let me close that. Here we are on week 4, dealing with 1D motion. And what I want to do today is, of course, cover what we're dealing with this week in terms of your assignments and what have you. And then I want to just give some basic definitions. And then on Thursday, we'll use those definitions to help solve some problems. Okay. So that's kind of how I'm thinking. Since we only get 1 hour and 15 minutes each class period, I'll introduce the concepts on Tuesday, solve some problems on Thursday, unless, we're dealing with a topic where I can do all of it on a Tuesday or all of it on a Thursday, but this week won't be like that. We'll meet today and then Thursday, and I'll cover concepts today, practice problems Thursday. All right. Oh, before I go any further, I'm about to jump in and forget what I talked about last week. I had put an offer on the table for anyone who wanted to solve a problem dealing with unit conversions and then bring it here to the class so that it could be shared. And I want to, honor that. So here's what I can do. Is there anyone who has a sample problem dealing with unit conversions that they wanted to share out with the class? All right. Well, that bonus opportunity is forever gone since nobody took me up on that. But, I did work several sample problems dealing with unit conversions last week. Of course, you can always watch the video to see the problems that I solved. So I guess I get to keep the bonus points in this case. All right. So now that I've honored that, let's move into the 1D motion stuff. So you can see here, we're starting to get to one of the major areas that we deal with in this course. This course, as I mentioned when we first got together, was that we deal with Newtonian physics, which is based in a large part is a study of motion. And that's what the word mechanics means when we say it in physics, motion. Okay, and all the things that go along with motion. And so we're taking our first step into that. And a large part of this course will be learning how to analyze, understand and analyze different types of motion. And so this week, we're going to be looking at one of the simplest type motions, one-dimensional motion. And we'll get deeper into what that means here as I go through the materials. So you can see that if we're going to describe a moving object, there are some things that you're going to be learning to do in order to do that. And that is, number one, what are the requirements for motion? How do we know that an object is in motion? There must be some things present that help us understand that. We'll see what those things are. Once we've established that the object is in motion, we'll describe it using certain properties like position, speed, velocity, and acceleration. So if the object is moving, we want to be able to determine those things, those properties of that moving object. Things like position, speed, velocity, acceleration, time. We'll look at that. That's a very relevant property. And we'll look at some counterparts to position and velocity, and that is distance and speed. And we'll look at the relationship between those properties. We'll look at motion graphs, because we can also use graphs to describe a moving object. And then, of course, we can always describe that moving object using calculations and equations, right? We'll look at a particular type of 1D motion, free fall. And we'll get an understanding of what is that and how do we describe a moving object that is in free fall. So those are the kinds of things that you'll be learning in order to describe an object that is moving in one dimension, or as we could always simplify that and say one direction, okay? And you'll find that if you get a good, strong grasp of these concepts on a 1D motion level, then you can utilize those same definitions in many instances to describe objects that are doing even more complicated type motions, okay? So this 1D motion stuff is setting the foundation for the properties and characteristics that you need to be able to apply in other situations when we deal with other types of motion. I can't go into this stuff without strongly emphasizing that all of the things that we're going to be doing in order to describe a moving object are based on motion. So we're not interested in things like color or, any of those touchy-feely kinds of descriptions, nice, small, large. But, there are certain things that we will want to do to describe a moving object. And in order to do that, you have to build on your understanding of measurement. Okay, so you can think of it now as you learned all that measurement stuff, and now you're going to have to apply it to describe a moving object. Okay. And I know I took a moment with those objectives, but it's so important that you understand, the scenarios that you're working with. Okay. So you have a few assignments on your plate for this week to get done by this Saturday. And that is your 1D motion discussion session. Remember, discussions are completed in Canvas. You post your responses to the discussion questions, and then you respond thoroughly to 2 of your classmates. The other thing you have on your plate for this Saturday is problem set 2. Now remember, problem set number 2 deals with last week's material. So last week we dealt with unit conversions. This week your problem set deals with unit conversions. Remember, the discussion is always on the current topic. The problem set is always on the previous week's topic, okay? And let me just highlight for you now, since you're kind of getting a little bit deeper into this problem set business, especially on problem set number 2, because this is a common mistake that students make and they lose points. If you do not show your work for problem set number 2, you will not get credit for it, okay? So that's the rules that we operate within this class. If you go look at the syllabus or under assignments and activities, the requirements for problem sets or discussions, you must show your work or I will not give you credit, okay? Remember, problem sets get emailed to me. I am still at this late stage getting emails from folks saying, I don't know where to find things. I don't know how to do this. What am I supposed to be reading? All those things, which means somehow they never found the weekly overviews in all of this time. And especially given that week 1 was the time frame for doing that kind of stuff, okay? So remember, problem sets get emailed to me, okay? And then there's the class questions forum where you can post a question and, it's a space where you can just have class related discussions with your classmates, okay? I do want to offer an apology to the class at this point, because I've been a little bit, I'm behind on some of the grading. I tried to get some things done last week, but I've been under the gun with a major project at work. And it's been taking up a little bit more time than I had hoped. But I am going to get to the grading for this class this weekend. This weekend, no matter if what, you know, no matter what happens, I'm going to get some grades out there for you beyond the week 1 grades that I posted. So apologies, you know, but as they say, work happens, right? All right. So Saturday, you have these items that you need to get done. Here are the resources that I've made available to help you with this 1D motion topic. I would encourage you to come out here and look at these materials that I provided. Chapter 3 in the textbook deals with 1D motion. And so what I did was I took the textbook and I pulled out chapter 3 and I put it here because that's where you need it. Of course, you know, if you go in the announcements, there's a link to the full textbook if you want to use that. Feel free. There are some videos, 1D motion videos. And I got an email from a student saying, well, what videos should I watch? If I bookmarked them, you should watch all of them related to the topic. There's some free videos that deal with free fall. That motion graphs video, we're going to take a peek at that Thursday, because by then I'll be, you know, kind of ready to talk about how we can use graphs to describe a moving object. And then, of course, you know, my supplemental notes, those are the things I'm going to cover with you. And then we'll take a look at some sample problems and the extra notes to kind of give you a feel for the kinds of problems you should be able to solve. And then I always get a question or two from students. What is this acknowledgement stuff? Well, I don't know if any of you have ever had to write a research paper, but definitely you're going to write a paper for me, a summary for me. And, you know, at the end of the paper, you always have to have a works cited page, a bibliography, references, well, however you want to call it. Well, that acknowledgements link that you see in every weekly overview is a page that I create, giving proper credit to those sources that I use to develop this this unit or overview. Okay, just to kind of answer that question, because students are like, well, what am I supposed to do with that? Nothing. Is there so that the world knows I'm not pirating anything. I'm using these resources legally. Okay, just to kind of, you know, put that out there. All right. So now I'll probably talk more than I wanted to this morning. Let me see if I can move this out of my way. Okay. So here we are in my notes. And I can't emphasize enough, you know, I hadn't mentioned it in a couple of class periods, but I want to focus you in on this, how to study, because we're getting to the point now where I start to get emails from students and like, you know, how do I learn this stuff? What are some things that I can do if these are the things that you should be doing in order to be successful in utilizing this and you know, grasping this material. All right. In other words, you have to spend time with this stuff. You're not going to learn it through osmosis, you know, and I can't open your head and pour the knowledge in. It comes, you know, got to put some sweat equity in it, right? And so here are the objectives again that I pull right from the weekly overview relating to this particular packet. And you see up at the top of there, I wrote that there's a heading that says kinematics. And one of the things we have to understand is, what is kinematics? Okay. So the word kinematics means motion. Well, I already told you we're studying motion here, right? So another word for the study of motion is kinematics. We want to give a kinematic description of a moving object. Okay, and you see, it is Greek in its origin, like many of the things that we utilize in this physics course. You know, if you recall the history lesson that was like part of week 2, excuse me. It kind of, you kind of know right from the start that the Greeks had something to do with this stuff. And so the ability to describe a moving object was coined, and that whole process started under the Greeks, if you will. All right. So motion, that's what we're here to study about, right? But here's the thing. We're interested in studying motion at this point without worrying about its cause. In other words, an object is moving. We don't care what made it move or why it's moving. We just want to describe it, the motion. Okay. And so they give the example of a bird in flight. If we were describing the motion of the bird that's in flight, we would be interested in looking at things like how it turns, rises, descends, without worrying about things like lift or the wind or gravity. In other words, don't worry about what's making it move. Just tell me about its motion. Okay. So kinematics, the study of motion without respect to cause. And so, of course, you and I know that we live in a three-dimensional world, but as I mentioned from the outset, what we try to do in at this level of a course especially is look at this motion from a simpler perspective. In particular, we're going to focus on one dimension this week, and then we'll get the tools that we'll need to be able to, describe more difficult motion like two-dimensional motion. But in here, we don't do 3D. We don't analyze the motion of an object from a 3D perspective. We strictly stick to one and two-dimensional motion, and so what we've got to do is, look at the things we need to understand to deal with this simplest case of motion. So they give you an example of an object traveling on a long straight railway. And so in that instance, we're dealing with an object that can move in only one dimension. And that one dimension can encompass the object moving, for example, forwards or backwards. So when we say one dimension, we mean things like left and or right, up and or down, forward and or backwards, those kinds of things, along a straight line. Okay, so we're looking at, in essence, the kinematics of an object that's moving linearly in a straight line. And so there are some fundamental parameters, properties. That's a word I like to use. There are some fundamental properties that we study in kinematics. Okay. And we use mathematics to help us express these parameters quantitatively. Remember, that's saying what? We use measurement. So things like position. So if an object is moving, measure its position. Measure its displacement. Measure the time involved. Measure its velocity. Measure its acceleration. All of the properties that deal with kinematics, we want to determine through measurement. Okay. We do need some notation to help us do this stuff mathematically. And one of the most important symbols that we use in this class is delta. We borrowed the Greek letter delta, and we use that to mean a change. inevitably, if something's moving, something's changing. And so we use the Greek letter delta to help us express whatever's changing. And so they give the example of a change in time. So our object is moving. We want to know how much time has elapsed, or how much time did it take, or how did the time change while that object was in motion. And so we would represent that as delta t. I always tell students, delta means change. Whatever that symbol delta is in front of, that's the thing that's changing. So if we put the delta in front of the t for time, then we mean change in time, or delta t, okay? If it was change in position, it'd be delta x. We use x for position, for example, okay? Here is one of the key parameters that, well, the key concepts that we need to understand in order to determine motion. Remember I said one of the things we're going to be doing is determining motion. Is the object moving? Well, that's a loaded question in many respects. We say, is the object moving? The next question is, with respect to what? Where are you measuring from? Okay. And so, you know, if we're going to determine motion, we have to have a way of specifying location, position. Where is the object? Okay. And so in order to locate an object, we provide its position, and we do that within a reference frame. The reference frame, you can think of it in a simple way, is where is the object starting from? What, with respect to what? Where are you measuring from? So I'll give you an example beyond the one that they give here. If I asked you, you're sitting at home listening, hopefully attentively, and if I asked you the question, is your house moving? Well, you might be tempted to say, no, my house is not moving. Or you might say, yes, my house is moving. And so if you said, no, my house isn't moving, then your reference frame is the earth, because with respect to the earth, no, your house isn't moving. But the person who says, I'm on the moon looking at your house, and from my position, from my reference frame, your house is definitely moving. So if you're going to say that an object is moving, you have to specify, where are you measuring from? What is your reference frame? Okay. And so when we pick a reference frame, a position that we can use to measure from, we do that, you know, so that we have maximum convenience. In other words, we try to pick a reference frame to make things simple. So they give the example here, another one, nice example. You have an airplane and its passengers. And it says the location of the airplane at any moment is conveniently described in terms of its position relative to Earth. And it says, but for the passengers that are inside, it's more convenient to measure with respect to the plane itself. You're in the plane is moving, you're moving. Okay, but if you're in the plane and it's moving, you don't feel the motion of the plane. In other words, since you're on the plane, with respect to the plane, you're not moving, but with respect to the earth, you are moving. Okay, so that idea of a reference frame helps us to establish motion. It's one of the things that must be present, and they give that example here with the plane. Okay, so you have to choose a reference frame in order to establish motion. Choose it in a way that makes that description as simple as possible. All right. So once you've established the location of your object or its position with respect to the reference frame, the next question is it moving? How do you know that? Because you, with respect to your reference frame, the position is changing. Okay. And when we look at the change in position of your object, we call that displacement. So the displacement is how does the position change? And you can see we have in the figure delta x, where we use x to specify position. If the position is changing, we call that delta x. Now, we don't want to mix that up with distance. Okay. Distance just tells us how far the object moves. Its total path, measure its total path, the length of its total path. Okay. So distance is how far. Displacement is how did the position change? Okay. So to give a nice example here, home and the store. If a person walked from their home to the store, they would have a displacement of 3 kilometers, and technically in this case, call it, say, forward, because a displacement does have like a direction on it, but we're not quite ready for that. But if they went from home to the store, their position changed by 3 kilometers. The distance that they travel, because we're looking at how far from home to the store, is also 3 kilometers. Okay, so the displacement would be 3 kilometers forward. The distance would just be 3 kilometers. If that same person turns around and comes back home, their displacement, the change in their position, is 0 because they're back where they started. So displacement looks at the difference between where an object starts and where it stops. In this case, since where it starts and where it stops is the same place, the displacement delta x is 0. But if they walk from home to the store and back, their distance is 6 kilometers. Okay, so distance measures the entire path. Displacement, look at where they started and where they stopped and take the difference. So they give you the mathematical or symbol notation for specifying. Quantifying means what? Measuring an object's displacement. And they tell you to find that displacement delta x, we must use the equation final position minus starting position. So x final means the final position, and x naught, that x with the subscript 0, you don't say x0, you say x naught. Naught means where did it start from? Okay, so the difference between where it stopped and where it started. All right, so final position, x final, minus starting position, x naught. And a lot of times they use that x naught because typically we try to set our reference frame so that our starting position is 0, because that's simplest, right? So it says, if an object moves from an initial position of 2 to a final position of 7 in a reference frame, then its displacement is 7 minus 2. Think of a number line. If a person goes from 2 on a number line to 7 on a number line, then its displacement is 7 minus 2, or 5. And we should technically say 5 to the right, or 5 forward, or 5 positive, but we'll get to that whole direction business. For now, the displacement is 5. All right. It says, for the reverse situation, where the object moves from a position 7, starting position 7, to a final position 2, follow the rule. It says what? To get the displacement, you take the final 2 minus the start 7. That gives us -5. So you can have a negative displacement. That negative sign is meant to specify direction. And because this displacement, it has a special kind of category that it falls in called a vector. We'll talk about that next week. So it says that displacement has magnitude and direction because it can be positive or negative. When we say negative, we're not talking about negative as in greater than, less than. Anytime you see a negative sign on a displacement, that's telling you that the object moved in the opposite direction. You could think of it that way. Right? A negative sign gives direction. Units. Well, inevitably, we have to deal with units. Why? Because all this stuff is about measurement. And in the metric system, the unit for displacement is meter. The unit for its counterpart, distance, is also measured in meters. So I can't just say 5. I have to be very careful and put a unit on it. 5 meters, -5 meters. If I'm measuring distance or displacement, the unit is meter. So the unit won't tell you. You have to understand how to find the property that you're whether you're finding displacement or distance. Okay. You can't just look at the unit and say, oh, that's a displacement. Nope, because that unit meters could be used for a distance as well. Okay. We're going to skip over this scalar and vector quantities. We're going to rely on this heavily next week. We'll come back to it. They're breaking down here the coordinate system. Remember, I said you need a reference frame. And so they give you one here. Since we're only dealing with one dimension, the object can move forward and backwards, right or left, up or down. That's one dimensional. And we use a horizontal line to help us specify this one dimensional motion. And the origin is our starting or 0 point. Anything to the right of that is positive. Anything to the left of that starting point or origin is 0. I mean, it's negative, excuse me. The origin is 0. Anything to the left of that is negative. Sorry. Okay. We could also use a vertical line. Just take the number line and flip it, if you will. And then in that case, we still have the 0 or the origin as our starting point. Anything above that is positive. Anything below that is negative, right? Up is positive, down is negative, okay? Measuring time. So see what we're doing now, as I said, is establishing the rules, the definitions, the background or the foundation that we utilize to specify or describe a moving object. And one of those important parameters is time, because it's the one thing that's, we know is changing, is not standing still, right? And so we need that. If inevitably, in order to describe a moving object, we need to know how much time is involved in that, okay? And so anytime we measure something, measuring time is involved in that, especially for the kinds of things we need in kinematics, right? It's important, not just from a physics analyzed motion perspective, it's important in terms of understanding events that take place in our physical environment, right? Like, 24 hours in a day, or sun, the movement of the sun or the planets or things around you. If we want to give an adequate description of how things move in our physical environment, time is involved, okay? And in the metric system, the unit for time is the second. I think we talked about that, when I covered the base units and properties. The base property is time, and the base unit is the second in the metric system. If we want to talk about how much time that elapsed, that's another word for saying, well, how much time between the start and the finish, right? Well, we use delta T to specify how much time changed or elapsed, or how long did it take. Okay. Wow. Sorry, there are people outside my office having a nice, lively discussion. Hopefully it's not too distracting. So now, if we're going to find this elapsed time, or delta T, how do we find it? Well, delta always means look at the finish and the start. So T final is our final time. T naught is our starting time. If we take the difference between the start and the finish, we found delta T. For convenience, a lot of times we set the starting time to 0. And then that way we just have to say, we just use T for time. Because if T naught is 0, when you subtract out 0, you just get T final. And rather than just keep saying T final, a lot of times we just say T. When we just say the time that it took is T, we're assuming that the starting time is 0. But I always tell students, the starting time doesn't have to be 0. It's just convenient if we set the starting time at 0. Average velocity and speed. So average velocity is a property that we measure for an object. And what it allows us to do is look at the displacement divided by the time. Average means take the displacement. Remember, displacement looks at what? Start and finish. And we divide that displacement by the time that it takes. So velocity is displacement per unit time. And it's a vector property because whenever you do delta X displacement, that's a vector. But we're not going to get into the vectorness. Just understand that average velocity is not the same thing as average speed, because average speed looks at the distance traveled divided by the time. So velocity is displacement per unit time, while speed is distance per unit time. Okay. And we'll see when solving some problems that the average speed is not always equal to the average velocity in terms of the size part of it. Because we know from our previous example, displacement can be 0 even if the distance is not 0. When an object moves and comes back to its start, the displacement is 0, so the average velocity would be 0. But if an object moves and then comes back to its start, its distance is not 0. Because distance means how far did it go. And so you can see here from that kind of definition, they aren't always equal. And this visual will help a little bit. If we went back to our visual here, okay, in this instance, going from home to the store and back, the displacement is 0. So how much is the average velocity? 0. Why? Because the displacement is 0, and it doesn't matter how much time it took, because anything divided by anything, if 0 is in the numerator, the answer is 0, right? But the speed relies on distance. So in this instance, the distance is 6 kilometers to go from home to the store and back, 6 kilometers. And how much time did that take? Maybe it took them 2 hours. Okay. Maybe from home, went to the store, did some shopping, came back home 2 hours later. So their speed is 6 kilometers divided by 2 hours, or 3 kilometers per hour. Okay. So be careful when you're finding these properties that you are using the right definition, because I see a lot of people confuse velocity and speed, because in everyday language, we use them interchangeably, but they're not. They're very different in the physics world. And we have to learn to use things accordingly, according to the proper definition. Now, whether you're finding velocity or speed, the unit is meters per second in the metric system. Now you see we abbreviated M for meters, per S for seconds, meters per second. So again, you can't look at the unit. If I tell you the unit is meters per second, you can't automatically tell me whether it's velocity or speed. You have to look at what is the object doing, okay? Instantaneous velocity and speed. And I'll just keep this simple. Instantaneous velocity is the velocity at any given moment. Instantaneous speed is the speed at any given moment. So like freeze frame, like you freeze time at that instant, what is the velocity? At that instant, what is the speed? Now, because the math involved in finding those two properties requires calculus. Anytime you need to use instantaneous velocity or instantaneous speed, I will give you those values. Or, yeah, give you those values. Okay. Acceleration. So now we move from where's the object? How fast is it moving and in what direction? Now, how is the velocity changing? Okay. So when we want to know how an object's velocity is changing, we look at the change in velocity per unit time. And that is called acceleration. The change in velocity per unit time is acceleration. Okay. Now the question becomes, well, how many different ways can an object accelerate? Well, for an object to accelerate, it could change its speed. You know, typically you say what? Accelerate and decelerate. Those are terms that refer to an object changing, you know, its speed, speed up, slow down. But an object can also change its direction and produce an acceleration. Okay. And we'll see that when we talk about circular motion. That's the easiest scenario where an object is changing its direction and thereby accelerating. You could think of it this way. If you put your car on cruise control, your speed is fixed, so you're not accelerating. But if you put your car on cruise control and drive in a circle, because your direction is changing, you produce a change in velocity, which results in an acceleration. Okay. So when we look at average acceleration, which is a property we most often will find, and we'll look at some examples of using that property on Thursday. You take the change in velocity over the change in time. And then we could talk about instantaneous property, instantaneous acceleration. Freeze frame is the acceleration at a specific instant, at a specific moment in time. What's the acceleration? Well, we call that instantaneous acceleration. And again, anytime you're using instantaneous properties, we'll have to provide them with you, provide it to you, because to find the instantaneous acceleration does require some calculus. But because we keep things simple here, those types, that property will always be provided. And if you're dealing with acceleration, the metric system unit is meters per second squared. I can't express that enough. The unit for acceleration in a metric system is meters per second squared. Okay. that unit gets beat up, banged up, abused so much in this type of course because students don't process that in order to correctly specify a property, you have to correctly specify its unit. And if you are dealing with acceleration and you tell me meters per second, that's wrong because that's velocity or speed. If you tell me meters per second cubed, I don't know what that is, but it's definitely not acceleration. But to be dealing with acceleration, you must be using meters per second squared in the metric system, okay? If you use another system, then the key is the time unit, whatever it is squared. So miles per hour squared or feet per second squared. A distance unit divided by a time unit squared, okay? We're not gonna get too much into this right here. You can kind of skip this screen because I try to keep things simple for you in terms of acceleration versus deceleration. I don't like that word deceleration. In physics, I want you to deal with acceleration, and that acceleration can be positive or negative. If the car is speeding up, for example, the acceleration is going to be positive. If the car is slowing down, the acceleration is going to be negative. And that's how we're going to use it in here, okay? We're going to use it so that we keep it simple. Acceleration is positive, hit the gas. Acceleration is negative, hit the brakes. The acceleration is positive, the object is speeding up. If the acceleration is negative, the object is slowing down. And those are the two scenarios that we'll deal with. We're not going to get too exotic and talking about, well, what if an object is backing up or this? No. Acceleration is positive or negative. Okay. And so we, as I said, want to utilize our understanding of the kinematic properties, distance, position, time, speed, velocity, acceleration, to help us describe the motion of our object. But just like we want to keep our motion simple at this point by looking at one dimension, we also want to simplify things by saying we can only work with things where the acceleration is constant. Now, I didn't say the position was constant. I didn't say the speed was constant. I didn't say the time was constant. I didn't say the velocity was constant. I said the acceleration is constant. Okay? And that means that if the acceleration is constant, the object is moving where its velocity is increasing uniformly. Constant acceleration. So by keeping the acceleration constant, we simplify the motion tremendously. Okay? Not only is it moving only in one direction, the acceleration is constant. So with those two constraints, if you will, those two boundaries, then we have something we can work with in terms of describing our moving object. Okay. And so we'll see an example of motion with this constant acceleration is free fall. And they're talking about that, the idea of, an object moving in one direction under the control of gravity, free fall. Okay. And so during that free fall process, gravity, which produces the acceleration, is fairly constant. So anytime an object is free falling, it is being controlled by gravity only, which causes the object to accelerate, and that acceleration is constant. Okay. All right. So these are the equations that we use to describe a moving object when its acceleration is constant and it's moving in one dimension. So if it's moving in one dimension and the acceleration is constant, there's a set of equations we can go to help us describe the moving object. Okay. And so you see listed there those kinematic equations for 1D motion with constant acceleration. Okay. So now let's take a look at the parameters in this equation. Anytime you see the parameters x in an equation, they're talking about the position. Okay. So you can see in that first equation, x, which is the final position, equals to the starting position plus the velocity times time. And then anytime you see v in that in an equation, that represents the velocity. Okay, so you see in the second equation, they're finding the average velocity. How do I know it's average? Because it has that little bar symbol over the top of it. And then that's equal to the starting velocity plus the final velocity divided by 2. That's how we find the average velocity when the acceleration is constant. In the third equation, well, you got a couple of things happening there. You got the final velocity, you got the starting velocity, the acceleration, and the time. So if I want to know the final velocity, I take the starting velocity and I add the acceleration times the time to that. And you want to know how fast? Well, you want to know how fast the object is moving? Tell me how fast it was moving when it started and how long it accelerated. That's the third equation. If you want to know the final velocity of an object, well, what velocity did it have when it started? And then how long did it accelerate? A times t. That's not at, that's acceleration times time. Okay. The fourth equation, that allows us to find position as well. Okay. So if I want to know where the object is, tell me, where did it start from? How long did it maintain the starting velocity? And how long did it accelerate? Okay, so you see what I'm doing. I'm taking those equations and I'm reading them in terms of what's physically happening. Okay, so the fourth equation, if I want the position of my object, tell me where was it at when it started? How long did it maintain the velocity that it started with? And how long did it accelerate? If I want to find position, I can go to the fourth equation. And in that last equation, it's very beautiful because it's a combination of the equations, the 4 previous equations, if you will. It allows us to figure out the final velocity if we know the starting velocity, the acceleration, and the displacement. Notice that very last equation, there's no time involved. We don't care. In that last equation, we don't need to know how much time it took. We just need to know those kinematic variables: velocity, acceleration, displacement. Okay. Now, you might be thinking at this point, wow, those equations look really complicated. Using them can be challenging, but here is what I do at this level of a course. I don't want you to memorize these equations at all. I do want you to know that these are the kinematic equations for constant acceleration. So at any point, if I ask you, what are the kinematic equations for an object moving with constant acceleration? You would give me these 5 equations. But when it comes to actually solving problems, we're going to approach it from a simpler perspective so that you're not having to utilize these equations in the equation form. Okay, and you'll see that on Thursday, how I will take these equations and use them in a way that's simpler for problem solving purposes at this course, in this course. Okay. Free fall. I mentioned that earlier, that, you know, an object falling in physics doesn't always mean the object is moving straight down. Falling could mean the object is moving straight up or straight down. But if it is free falling, then it means the only thing influencing that motion while the object moves up or down, I like to say free fall is vertical motion, because vertical could mean up or down, right? And so if an object is free falling on Earth, vertical motion on Earth, gravity is producing an acceleration that is constant, 9.8 meters per second squared. If you're on planet Earth and the object is free falling, meaning what? Vertical motion under the control of gravity only, no air resistance, the acceleration the object feels is 9.8 meters per second squared. Okay. Notice, to describe the free fall motion of an object by specifying acceleration, I didn't talk about force at all. Gravity does produce a force, but gravity also produces an acceleration. And when gravity is the only thing affecting the motion, we call it free fall. And that gravity on planet Earth is 9.8 meters per second squared. Now, if you went to the moon and an object free fall, you know, was free falling on the moon, the acceleration wouldn't be 9.8 meters per second squared. It'd be about 1.7 meters per second squared. Okay, so you see, because the gravity can change from one planet to the moon or whatever, when an object is free falling, you have to use the value of gravity on that planet. Okay. All right. Now, if an object is free falling, all we do is come back to these equations. It's free falling. And we take A and replace it with minus G. I know in the notes here, it says put in A equals G, but they're just talking about the magnitude. And remember, because it's falling, we always have to add a minus sign because that tells us direction. Okay. So the easiest way to think of it is, if you're going to solve problems for free fall is an example of constant acceleration. Free fall is an example of 1D motion because the object is moving vertically under the control of gravity only, which produces a constant acceleration. When you want to analyze that motion, you can use these same equations, except replace X with Y. So everywhere you see an X, put in a Y, because we use Y to specify vertical. And everywhere you see an A, replace it with minus G. Okay, so you can take those equations and transform them and utilize them to analyze free fall motion just by making those simple changes. Okay. Now, graphical analysis of motion, we're going to get to that on Thursday. We'll talk about that on Thursday. We'll also solve some problems that deal with 1D motion. And we'll watch a video that discusses this whole graphical motion piece. All right. So I know I've talked quite a bit now. I want to stop the share. And I want to thank everybody who's been, so attentive this morning. And of course, I never like to close shop without asking, what are your questions?
I don't have any.
Thank you, Tiffany.
I don't have any either.
Thank you so much. I really appreciate the chiming in. It helps me to know we're on the right path here. So if there are no other questions, we're done. Just remember, if you're going back over this stuff and you have some questions, reach out to me. I'm always happy to help. All right, so I'm going to stop the recording now.